So I'm Jon Hodgson. I'm a performance and a management expert for Riverbed Technology. I've been doing this for about 12 years. I've helped hundreds of organizations, from space agencies and banks and enterprises, solving really squirrely issues. And I thought this would be an interesting opportunity to talk to a room full of developers who have often seen APM tools and profilers tell them that certain methods are slow, and you try to solve these issues and you're unable to. And hopefully what I'm going to show you today is something you can take home with you, and next week solve some percentage, you'll be able to solve some performance issues that you've been having in your application so far. And actually, to start with, our buddy Duke here, who we know is a Java mascot, he's being blamed of slow code, and hopefully at the end we'll be able to absolve him of all crimes. So the goal here is to fix performance without touching the code. So this is a stacked area chart of showing components of delay for some transaction. The orange means it's code. If you saw a lot of red, it wouldn't be your problem, it would be database. But here we see a whole lot of orange. We want to get that 1,500 milliseconds down below the SLA. And we can do that without changing any code whatsoever in certain circumstances. And I want you to be able to get the skills to be able to determine when that is. Do any of these sound familiar to you? Do you have application issues that linger over time, they come and go, but you're never really able to pinpoint them? Having simultaneous issues in many unrelated transactions, so for some reason, all of a sudden, login and account portfolio are all slow and so on. Application issues which roam from tier to tier in the environment, so you can't particularly determine, is it in this app server or this remote web service and so on. And issues which move around your code. Sometimes it's in one method, sometimes it's in another. Things you hunt for, you're never able to find. You try to resolve them. No matter what you do, you can't. And most importantly, your end users continually complain about performance issues, and not without trying, you're not able to solve them. So I want to talk about phantoms. So phantom, a ghost, something apparent to sense, but you can't touch it, right? No substantial existence. You know it's there, but you can't quite put your hands on it. It's elusive, it's visionary, and my favorite, it's something that causes continual dread. And when we're responsible for the performance of an application and we're unable to do our job, there's a lot of dread there. So how this ties into our jobs as developers and performance analysts, this term, performance phantom, this is my term, which describes intermittent application issues which have inconsistent symptoms. And that word inconsistent is critical. Issues who the apparent root cause actually winds up, once you've figured it out, to be a symptom of another issue. And a seemingly unrelated set of application issues which ultimately are due to an overarching root cause. So it looks like many different things, but in fact it's actually one common thing. So I'm going to use a couple of examples of just, pseudocode to show this phenomenon. So here we have a URL, an account details page, and inside it's very simple. There's 3 methods that make up this total 1.5-second response time. Now when we look at this, they all equally take 500 milliseconds, and this is a normal transaction, so what we expect to see in our code if we run a continual loop of it. But then maybe at some point in time you get a report of slow code and you look at your logs and so on and you determine, I have one execution that took 3 seconds, and the bulk of the new delay is in that middle method, is in format details. And this has now been the reason that my code is 2 times slower. And we see this all the time, and developers go into the code, they try to figure out how to optimize it, they'll take out some string operations, whatever, and yet this problem keeps occurring. So now we look at some additional executions of this same URL, and they have delays in different places. So they've both gotten 2 times slower, but it's not in the same method. And this is when you could start sniffing out you're dealing with a phantom. So here we have 3 completely different methods for the same transaction that are periodically causing slowness. So why is this not consistent? And again, that word consistent and inconsistent is critical here. If we take these transactions and we now look at them from an absolute time perspective, not relative, and we compare this to something it depends upon, and right now let's not worry about what this resource dependency is, and we say, okay, if we look at that dependency, at some point in time, it's saturated. When that thing becomes saturated, any code that coincidentally is running at that moment is going to be impacted by that. It's going to block, it's going to stall, and anything running is going to be delayed at that point. So the execution time of method start to method end increases, but the processing time, the colored pieces we see to the sides of waiting, actually doesn't. It's still doing the same amount of work. And this is the clear indicator that it's not your code. There's nothing you could have done to make it faster because Your code is not the reason it got slower. The way to solve this and to think about and identify these issues is to always consider your code in the ecosystem of the application. Now, I have Java.NET as an example. I could have added Node and other languages as well. And for simplicity, I'm going to use some Java examples, but this applies to any language, and in many cases, more than likely anything you guys are writing. So this code runs in a virtual machine of some sort, a JVM, CLR, and it has dependencies within that container. Things like heap that it has to rely upon that needs to be there for it to perform well. And those containers, which are ultimately processes of an operating system, are now dependent on the OS resources, so CPU and RAM and memory and disk I/O and handles and threads and so on. Now in this example, where I have two different applications on a common shared OS instance, the .NET app could do something that affects the Java app because they are connected, they are related, and it's not impossible for that to happen. And if we separated these two applications, and if we made them VMs, those VMs share a hypervisor. So now, even though they're two separate OS instances, they still have the ability to affect each other. And we have to be cognizant that the ecosystem I'm talking about doesn't stop at the OS instance you're SSHing into or logging into. So I'm going to give you a series of examples that illustrate this concept of phantom delay. So here I have a hypervisor that has two VMs, two operating system instances, that each have one JVM. And what you're going to see here is that the orange blocks are some method, the same method running in a loop, the same method in both JVM. And the two green bars are the state of garbage collection and hypervisor state, whether the hypervisor pause. And these are just two examples that you'll see can cause blocking issues. So at some point, the hypervisor gets a demand, maybe some other VMs we haven't illustrated here, for CPU. And it doesn't have enough because it's overcommitted, and these resources weren't guaranteed. So it has to steal resources from somebody. And in this case, VM number 1 gets its CPU cycle stolen. And when this happens, the VM pauses. It is as if you pause the operating system temporarily. And so you see this one method execution gets longer, even though it's not doing anything different than its three friends. And then afterwards, everything goes back to normal. Now, in the real world, this is typically going to happen for fractions of a second, which means it's not even going to be easy for you to monitor this on some sort of monitoring tool that's pinging every second, because it's going to happen in the middle. Instead of having 1,000 milliseconds of clock time, maybe you only have 800 or 200. In very extreme circumstances, you could see multi-second pauses, and that's when it becomes obvious. So let's take another example like this, where we still have the same number of JVMs, but they're on the same physical machine now. So now, when that hypervisor pause occurs, because those JVMs are processes in the same operating system, which is paused, both JVMs simultaneously pause. So whatever code is running at that time is going to be paused. So if you see issues in your environment that are happening in tandem in unrelated resources, because those two JVMs are not the same containers, they should not have synchronized behavior. And if they do, there's got to be something that links them together that's causing that synchronization. Now, it could be something, some dependence on a shared session state or something like that. It's not always this, but this is what you need to look for. And then again, everything's fine. So hypervisor pausing is one potential form of contention. I want to talk about garbage collection and dispel some myths that occur here. So Java and .NET garbage collection, as well as JavaScript and Node.js and any other language that has managed memory, will stop the world. So what that phrase means is that all non-GC threads get paused. The threads that run the code that you write get stopped until the GC finishes. So any method that is running at that time is just going to get slower. And I want to make this perfectly clear. Contrary to popular belief, all garbage collectors stop the world. That includes your fancy concurrent mark sweeps and the new garbage first G1. They all do. And they do it in JavaScript, and they do it in the browser. Now, they do it to different degrees, which we'll talk about why you might not think that. And the other myth is that minor GCs do not cause pauses. They absolutely do. They're just smaller and harder to notice because they might be for fractions of a second. But if you add up enough of these little things, it's death by 1,000 paper cuts. So let me show an example of GC pause time. So we have these different collectors. They're going to have different effects on throughput and response time depending on how they're configured. And the trick here on which method you pick is when you're dealing with transactional systems with end users, the longer pauses at one pause are going to be more noticeable to an end user. So here's an example of some piece of code that we're running in a constant loop, the same method over and over, and the state of the GC. So this is the best state. There's no GC occurring. I've got 33 executions, and the min and max response time is 300 milliseconds. That's my starting point. And now we use one of these sort of legacy or original garbage collection mechanisms, and there's one massive pause in the middle. So my throughput gets halved, and my maximum response time goes from milliseconds to now over 5 seconds, 18x increase because of one GC. Now, only one transaction, one method execution gets affected by this, so it's a small percentage of transactions affected. But boy, if you were that one user doing that one thing, you'd be pretty unhappy of this massive 18x increase in response time. So if you pick some other GC mechanisms, you may have more but shorter pauses. So in this example, I've gone up to 1,300 seconds, 4x increase in that one method execution, which is an 18%, it's affecting 18% of transactions. So more users are going to be unhappy, but they're not going to be quite as unhappy. And now these more modern mechanisms, like the concurrent mark sweep and so on, are going to do a lot of little pauses all the time. And they'll be fractions of a second, milliseconds. So here my throughput is still halved, same exact throughput, but all my methods are now twice as slow. The mins, the maxes, there's no inconsistency in response time. There's no slowness for someone to notice because it's always slow. It's still fast maybe perceptually, but there's no change in behavior, so there's nothing for them to react to. So 100% are affected, but it's only a 2x increase in whatever you coded. So I'm illustrating this to prove that you have to work very closely with the people who are running your VMs, your JVMs and CLRs, or whoever's managing your Node.js systems as well, that tuning these settings can have a marked difference in how your code behaves. The very same code on two different systems could behave completely differently depending on these factors. So let's put this back now to one of these flows where we see the effects of GC. Now in this case, it's a little bit different. Every one of these 5 threads has a different type of code it's running, 5 different methods. Method 1 on thread 1 is running very fast, so it's got 18 loops in this period of time. And then conversely on method E on thread 5, it's just something that's more that does more processing. So imagine that method A is doing a variable get or a variable set, something like that. And then method E is doing something like calculating pi to a billion digits, something more complicated. When a GC occurs, they're all paused. And they're all paused for the same number of absolute milliseconds. So their response time just gets extended for however long that pause was for, then everything goes back to normal. But the relative execution time is where you notice this. The little guys get 11x slower, whereas the really slow one is only 3x slower. As troubleshooters, when something's slow and you're trying to look at what's changed the most, you're going to go, method A, why did that get 11 times slower? Let's try to optimize that, which is going to be the hardest thing to optimize because it's already very fast. It might not do much. And this is why you start seeing phantoms. But the trick is, did you have a lot of different things that changed at the same time, even if they didn't change by the same degree? And this is what you have to look for. Because typically speaking, if it's a problem with the code that is not related to the infrastructure, you're going to see it isolated in a particular area. And now to make matters worse, we run in a world that's virtualized, and you can have compound delays. So everything's fine. And then JVM1 now says I have to do a garbage collection, so execution 3 in JVM1 gets longer. And then the OS, for whatever reason, gets paused because the hypervisor needs more CPU, so now both JVMs get paused. And once that pause stops, JVM1 is still garbage collecting, and then it's done. So here we have the exact same code, and it's 7x slower on one and 5x on the other. And just illustrating that these types of compound issues can occur. So I know I'm using the examples of garbage collection, I'm using examples of hypervisor pause. There's many others, right? There could be disk queuing, so IO wait, network IO wait, and so on, thread blocking, whatever. The idea is to consider that multiple things can be happening at once, and that's why you're seeing these results that don't make sense. So let's talk about a real-world example here. So I had a customer who had been trying to solve a problem for a long time. They had used a variety of APM and monitoring tools and could never get to the answer. And they said, look, we've got 2 apps. We've got a .NET app. We've got a Java app. Don't worry about the Java app, different app. but the .NET app has slow response time, and we can't figure out why. And since I don't trust anybody, it's always trust but verify, we checked into the architecture, and sure enough, they both lived on the same hypervisor. And what actually was happening as a play-by-play was that the Java app had greater demand on something that it did. It had more throughput. And when that occurred, it did more GC. And when more GC occurred, it used more CPU, which put greater demand on the hypervisor. And now, because that's happening, the .NET instance gets paused by the hypervisor because it needs the CPU cycles. So now the .NET response time goes up, and the throughput goes down. So here we have a situation where GC in one application on a different box is actually causing application pause in another box by way of OS contention. And what we have here is a symptom in the .NET app and the root cause being in this other application that was owned by a different group, a different set of developers, but sharing a common infrastructure. And again, chasing the symptom, you'll never actually be able to solve the problem. So in that initial example where I showed that we can make things a lot faster, let's see how we actually did that. At the top, we see the slow response time. Now, the metric I compared it to, and this was in my product, but there's other products that can do this, other ways you can use, in this VMware environment, you can use the VMware tools, the out-of-the-box ones. And this CPU denied time, it might be ready time if you're looking at vSphere, indicates that the VM is paused for some period of time. Now, this should be around 0 to 2%, honestly, as close to 0 as possible. But sometimes I see 15%, 40%. It's really bad. So when we know that that's happening, there is no doubt that any code running at that time has gotten slower. So I am not going to try to troubleshoot. You fix the first things first. I'm not going to try to fix the server response time by looking at code at this stage. I have to get the CPU denied down. Similarly, if it was garbage collection, I have to get that down first. So at this time, one point I want to make when you're dealing with an issue like this is that you cannot trust the operating system metrics when you have an issue like contention here, because it doesn't know what its maximum gigahertz is when it's getting gigahertz taken away. And you'll see later that the OS was totally confused about what its results were. So you have to have the right tools that are looking right at the source. The way we resolved this was the initial configuration had the critical server, the one running the mission-critical app that affected the bottom line of the company if things got slower and users cared, with a whole bunch of IT things, security scanners and backup servers and so on. And they were all sharing the same set of resources, so one could affect the other. We then split these into two completely different resource pools, which ensured that the utility servers can't affect the mission-critical app. So that when the security scanner does an hourly security scan, it's not going to be able to have an impact potentially on the critical server. And the way that we do this is by setting either resource reservations, where I guarantee I get X number of gigahertz, and ensuring that I don't have limits, which mean even though I have 2 cores that are 3 gigahertz apiece, that you've only given me 4 of those 6 gigahertz. And what ultimately happened when we did this was that when we made that first change and we removed a CPU limit, so when we looked at this customer's app and they swore up and down, we're given 2 cores, well, we found out, no, you actually had about 80% of 2 cores. Actually, it was about, I think, 60%. And by removing that limit, which removed the pausing, response time got 6x faster. But we still see it be thrashy, so we made another change, which was doing a reservation. And we said, listen, VM team, you're impacting my app. I want all 6 gigahertz. And the moment I did that, problem went away. Response time was better, throughput went up, it was doing more work, and the OS claimed that CPU went down because it didn't know what it was talking about. From a gigahertz perspective, it went up, but from a relative perspective, it didn't. So to verify the improvement, we always want to make sure that we can compare and contrast, and we saw that across the board, the app was faster and throughput was better. And the way to determine if you have a root cause or a symptom is to not just look at a couple of the slowest things. You have to look at a lot of transactions collectively, determine if there's consistency with your slowness or inconsistency. And the rule of thumb is if you see a single dominating method, it's something you're going to need to fix in the code. But if a lot of different things are getting slower, or different sets of things are getting slower, and there's not a discernible pattern, then you're looking in the wrong place and you're dealing with a phantom. So know that phantoms exist, troubleshoot in the context of your environment, know that your code can be affected by some larger issue, and ultimately ensure that if you have mission-critical apps, just avoid this altogether, have guaranteed resources. So hopefully you can go home and do this yourself and fix some of your issues. And our buddy here, all charges dropped. That means you too, no more blame. And thank you for your time. Have a good rest of the conference.